So now I'm going to give you a definition of electric potential. And as I give it to you, I want you to think about this. Imagine you have a positive charge here, and you have another tiny little positive charge that you're moving from a point A to a point B. And the point A is like basically infinitely far away, but you want to get it to be closer to this charge here. Now it's going to take you some work, because if you're having to push this charge, the charges don't want to be together because they're both positive. And so it's going to take you some effort to get it from here to here. That effort per unit charge is thought of as the voltage. It's kind of like the work per unit charge is the voltage. So the work required to move it from here to here, the bigger this charge A is, you can imagine, the harder it's going to be to push it closer to this other charge that's fixed right here. This charge here is going to be fixed in location. Somehow it's pinned down. So this one's going to be like, oh, I got to push it up the hill. And the bigger it is, the harder it is to push up that hill. This equation basically tells us the amount of work per unit charge that it's going to take to get the charge to go up this electric field hill from point A to point B. So let's think about it like that, and let's see if we can come up with an expression for that for a point charge. How much work it's going to take to get another point charge to move from infinitely far away to it up to something closer. So this point A is basically a way of saying infinitely far away, and then point B is like saying our final distance r, which I'll call r0. That's the distance away from the charge that we're trying to get the other charge to be. All right, so I'm going to plug in the expression for the electric field. It's equal to k times q divided by r squared. I'm going to plug that into this right here. And this dl refers to each little element of distance that I'm having to push this charge up that hill. And since L is kind of like, it's in the r direction, and I have to have the same variable that I used in this variable of integration as I'm using in this expression here, I'm going to say my dl is associated with the dr. All right, so I am going to write this as v equals the integral from, and I'll put in infinity to r0 here, of k times q divided by r squared dr. So that's where I'm at with all of the substitutions that I've been talking about. Now I'm going to pull out my constants. This is going to be equal to minus k times q integral of infinity to r0 1 over r squared dr. Now hopefully you remember seeing this integral at some point in your past. You may not remember how to integrate it, but the way we integrate it is it's going to be equal to the integral of 1 over r squared is minus 1 over r. Because this is r to the minus 2, so it becomes r to the minus 2 plus 1 divided by minus 2 plus 1, which is minus r to the minus 1, which is that. Okay, so let's continue with this. Then we have minus kq times minus 1 over r, where r is evaluated between r0 and infinity. And if I simplify this, it becomes k times q divided by r, evaluated between r0 and infinity. So this becomes k times q divided by r0 minus k times q divided by infinity, which this is really, you'd have to take a limit here to make this work right, but this essentially becomes 0, because whenever you divide by a big number, you get 0. So the answer for my potential at some distance away from a charge is that it's equal to k times q divided by the distance between the charge and the point we're interested in. That's the value of my potential at that point. So if I have a charge here, let me make it a positive charge. The potential some distance away from that charge, some distance, I'll call it R0. Doesn't matter what direction it is. It can be above it, it can be below it. Because potential doesn't have a direction, unlike electric field. It's just a value. It's a scalar number. It doesn't have a north or a 30 degrees north of west or anything like that. It's just a value. So it's going to have the same value at any point this distance R0 away from that charge. And that value it's going to be is this. So the closer I am to a positive charge, the smaller R0 is, and the bigger my potential is going to be. The further away I am from that charge, the bigger R0 is going to be, and the smaller the potential is going to be. So when you're really far away from the charge, you're at a potential of 0. When you're close to the positive charge, you're going to have a much higher potential. And I'll give you an example of this, but the potential is a value in volts. Okay, that will do for this video.